Today, we're going to be answering questions that came in on our contact form at acservicetech.com and also in the comment section of the YouTube videos. So I'm joined with my good friend, Ty Branaman, and he's here to help us answer all these questions. So I'm really excited to hear what you have to say.
I'm excited to see what these questions are, and I love it when you guys ask questions, so let's get to it.
So a technician by the name of Donald asks, what's the difference between silver soldering and brazing?
Oh, temperature. That'd be the easiest start. There's so many details in that, but we have brazing is going to be able to handle more vibration. It's generally a stronger joint, whereas the soft solder can handle a higher pressure, but it can't handle the vibrations as well. And it also goes down the code. Some codes, some local municipalities do not allow the soft soldering, and other places, we will allow it.
Yeah. So there's also the whole flux situation. And so when you're dealing with solder, you have to put a flux in, and that flux could be a creation of acid inside the system because it's not going to be exiting the system. So that's an issue. And the nice thing about silver soldering is you don't have to flow nitrogen through while soldering because you're not at a high enough temperature to really need it. But the reality is it's not that hard to just go ahead and flow nitrogen through at 3 to 5 cubic feet per hour while brazing. And the reason we do it while brazing is so that we don't have oxidation occurring inside the tubing. And so we don't have that maybe gumming effect or clogging the strainers or clogging of filter dryers or a lack of lubrication at the compressor. So there's a lot of reasons why you would or wouldn't do this.
I know there's a huge argument and a lot of personal preference on that. My personal preference is for sure brazing. I know once I braze a joint, I've never had to go back to anyone, but I've had to go back to a whole lot of soft solders. It's easy to fix a bad braze joint, but it's very difficult to fix a bad soft solder joint. And a lot of TXVs I've taken apart because I want to see what caused that TXV to fail will end up having that flux and having all that green stuff inside of that TXV from the soft solder, from the flux of that soft solder. So me personally, I don't like it, but I know some people that do it and they do it right, but it's a skill. It takes, I think, more skill to do soft solder correctly than it does do brazing correctly, but my opinion.
Yeah. Yeah. I mean, you could have larger tolerances, meaning like a large hole. Maybe it's a swage too big, or they're putting a copper pipe that's not the correct size onto a smaller one, and they're able to get away with it with the brazing. And you definitely can't get away with that when you're silver soldering. And you bring up a good point, Ty. And a lot of the manufacturers are not silver soldering these evaporator coils together. And so they're just brazing them from the factory. And they use those braze rings a lot of time in order to get a good joint. So yeah, great.
And now we have a whole lot of other options. Now there's different types of mechanical fittings that push together, that mechanically lock together with different wrenches. And then there's the press fittings now of multiple different brands. And no matter what you do, there's going to be a pro and con to every single thing. There's no one perfect answer for everything. And the big thing is, just to stay open-minded about it and read instructions. And it takes skill and practice.
Yeah. Practice. Yeah. You should be practicing constantly. Absolutely. Say at night, if you're going to be practicing on, say, an aluminum coil. So now we have aluminum and we need to be able to fix holes in that. And so it takes a lot of practice. You don't want the aluminum to collapse on itself. And so practice.
Absolutely.
We have a technician by the name of Matt asking, why would a run capacitor blow twice in a matter of just a few months?
Well, my opinion is going to be it's probably was a lower quality run capacitor, right. Or maybe it was a good brand and every manufacturer, everything made has failures. But that was definitely going to be a bad capacitor. So that's internal failure, in my opinion there.
Yeah. So you don't think that could have something to do with overheating because it maybe over a period of time, but it's probably, I think you're right. It's probably some type of manufacturer failure. It could be heat, but it would have to be an excessive amount of heat, but it just doesn't have enough, say, runtime there. It is possible, but I've even seen where the welds, even on the top of the terminals, have fallen off of the capacitor. It may not be the actual foil on the inside. It's just a connection to the terminals. Yeah.
Exactly right. I've seen capacitors bad right out of the box, brand new before, right? Straight from the supplies, not even rattling around in a truck. They've been bad. Yeah. So absolutely, those are some of the things I look for. And I personally like to use USA made capacitors. Yeah. There's two different brands out there that I know of, maybe more, but I know that when I put that in, I know that that's going to last. And again, everything has a failure. There's nothing that's absolutely 100% perfect, but we reduce those, right? I don't want to go back to that customer's house again, and they don't want to call me back again.
Right.
So for me, even if the capacitor is twice as much, it's still absolutely worth it.
Yeah. So just for everybody that's listening, Things that cause a capacitor to fail are heat, just how it was manufactured, its life cycle, possible corrosion on the outside, eating into the inside. So those are some of the factors that could cause a simple run capacitor to fail. And we do have a dielectric solution that is being used now that is less toxic, or it's not toxic. And so, but it doesn't seem to hold up as well as far as heat dissipation and allow the capacitor to last for a longer period of time. So. Thanks.
Absolutely perfect. You said all the things that are important for capacitor right there. 100% agree.
So Henry asks, what's the fastest way to pull a vacuum?
Well, that's a loaded question. There's a lot to that. I would say the shortest answer would be the least amount of restrictions as possible, largest hose as possible, and good quality, clean vacuum pump oil.
Yeah. So even if the vacuum pump oil looks like it's clean, a lot of times it's not. It's saturated with water. And if that's the case, it's not going to be able to pull a deep vacuum. And inside the pump, the pumping mechanism is sealed by the oil. And so if it has water in it, it's not going to make a good enough seal to be able to pull that deep of a vacuum.
That's exactly right. I've seen technicians that change their vacuum pump oil when it fell over in the truck. And that's not a good number. You can actually put your micron gauge on that vacuum pump alone and pull a vacuum to see how low your oil can get to. And I want to make sure it's pulling down like 50 microns. But yeah, make sure that's a big thing that's overlooked. And then the next thing is hoses. Make sure you got vacuum rated hoses and a large hose, and then make sure you're pulling those restrictions out, such as valve cores, things like that. Because if you're trying to pull, people got like to get a really big vacuum pump. They say, if I get this bigger, awesome vacuum pump, it's going to be better. But then they're restricted by these little bitty hoses, and they're trying to pull through that Schrader port, and there's so much restriction in there, it's too much of a pressure drop. It takes too long to pull that gases and the moisture out of that system through all those restrictions. So yeah, I think the vacuum pump oil, absolutely biggest overlooked thing, and then hoses and restrictions.
Yeah. So one of those restrictions is pulling through a manifold. So one of the most frustrating things for me back when was vacuuming through a manifold gauge set. I'd be thinking about it, just getting ready to go and do the vacuum. I'm just like, please, be able to pull down below 500 microns. And I just didn't understand why I was having intermittent problems. And it had to do with gaskets. The manifolds weren't built to be pulling a deep vacuum on, and their seals are not really made for that. So it doesn't take very long to use a charging manifold and have a leak in it. And so the other thing is, you mentioned pulling the valve cores out, and use valve core removal tools. When you put those back in, make sure it's positive pressure when you're putting them back in. Don't try to put them back in during the vacuum. But anyway, you want to have the vacuum gauge as close to the system as possible so that you can read the true vacuum level, and just use large diameter hoses, and then they can just reduce down the least amount of connections possible, like you said. So that's great.
100% agree.
A technician by the name of Lauren asks, how far down do I need to recover the refrigerant to?
Well, the simplest answer is always follow the EPA requirements and laws. You'll see that if it's commercial, residential, over 200 pounds, less than 200 pounds, if it's ozone depletion or not, they have very, very specific rules. I don't have those memorized. I always have to refer back to it.
Yeah, so the R22, R410A, like if it's below 200 pounds presently, if you can pull it down to 0 PSI, that's correct. But what a lot of people think is that they pull it down to, say, 0 PSI, and then they're good, and that's it. Well, the problem is, once you shut the recovery machine off, and it has a check valve. So some that don't have a check valve, you're gonna have to shut the tank off first, then immediately turn the tank off, then turn the machine off, and then check the pressure to see it rise. Well, the problem is, you pull it down to 0, it's going to rise because a lot of that refrigerant is still trapped in the oil in the system. So just because you pulled it down to 0 PSI, that doesn't matter. You need to then turn the system off, monitor pressure for, say, 5 minutes, see if that pressure rises. If it does, you're going to have to recover that refrigerant again.
And that's really going to be for a safety issue. Now, we want to recover that refrigerant because the more refrigerant we recover, the more we have to use later. Also because it's the law, we have to do that. But really think about it for our own safety. If I pull it down to 0 PSI, there's still 15 pounds of pressure of actual atmospheric. So atmospheric pressure, 15. We pull a vacuum, we add refrigerant in to get it back to 0. See, if you pull it down to 0, there's still 15 PSI of refrigerant pressure in there. And then it's also mixed with the oil in the compressor in the system. So when we start brazing or working on that system and heating those pipes up, temperature goes up, pressure goes up, the refrigerant starts boiling out of the oil, and then that comes across these pipes. It goes across your torch, it ignites, it's also carrying oil with it, and it becomes a safety hazard. So regardless of the importance of the environment, the importance of the fact that it's our law, the importance of having it to recover for our own safety. I want to recover down as low as I possibly can so I don't have that refrigerant flashing out at me, because I've had that happen. I've made that shortcut before, and it was quite an eye-opening experience. I saw the light.
Yeah, that's not good. So yeah, you don't want to breathe it in, the whole 9 yards. It's a big deal. So we're recovering because we have to do work on the piping. So whether that's the line set piping or whether that's the system, like we're moving the system, and you're going to have refrigerant trapped with the oil, and you got to be cautious and careful with that. Another factor is, should you recover down below, say, 0 PSI if you have a refrigerant leak? And so that's an issue too, because you shouldn't do that. So basically you just want to pull down to 0 and that's it, because you could end up pulling air through the leak spot into the recovery bottle, and then you're contaminating just the refrigerant in your recovery bottle. And so if you have a leak on a system, you can recover it down to 0 PSI. You're still going to have to turn the recovery machine off, monitor the pressure, see if it rises. You might have to recover again. And then basically each time you're only recovering down to 0 PSI because you don't want to pull that air into the tank.
That's exactly right. There's also a trick we can use that works to speed up recovery, but especially if there's a leak in there, we could actually heat up that refrigeration system, running the blower door inside. Outside, we can put a tank heater on the base of the compressor or use a heat gun on the compressor and heat the compressor specifically where the oil is. Yeah. And if we're doing that, we're keeping the refrigerant boiling out of the oil, so it keeps the pressure up. So we're doing two things. We're not pulling air in if we have a leak, and it's also speeding up the recovery because our suction pressure is higher. So those are some little tricks that we can do to make that recovery faster, and we don't have contamination in our tanks.
Yeah, I love the trick of just being able to turn the thermostat on fan mode. So if you have a split system, you can just pull the disconnect outside, turn the indoor thermostat on air conditioning mode or fan mode or whatever, because basically you're going to be running that heat across that indoor coil, and you recover fast, and when that happens, you're not getting all of that refrigerant out of the oil. You want to just basically heat, add the heat back into the refrigerant, and any oil that's in that indoor coil, you want to boil that out. So those are great points.
And we talked about vacuum in the past, but if we also pull those Schrader cores and use a large hose when we're recovering, it's amazing how fast that will speed the recovery as well.
Yeah, great points. A technician by the name of Edward asks, on a mini split that has multiple indoor units, is there one EEV per indoor unit / refrigerant loop?
Now, from what I've seen in my experience, yes, but I want to say never take that for granted, because the equipment's changing constantly. They're coming up with new ways of doing all sorts of things. So everyone that I've seen, I would say yes, but I still want to refer back to that manual, because the piping in these systems, even in the same brand, can change from time to time.
Yeah. So say it's a multi-zone unit and it does not have any branch box. So if it has branch box, it's the EEVs are all going to be there. If it's a multi-zone system without a branch box and the line set goes from the outdoor unit to each of the individual indoor units, you're going to have an EEV per zone in the outdoor unit. But like you said, you could have an EEV controlling maybe 2 indoor units in the future. We don't know, so you're really going to have to pay attention to all that stuff, because those indoor units don't have an EEV on them. So the EEV, the metering device, electric expansion valve, may be found in a branch box if you have a mini VRF, so that's a variable refrigerant flow, or maybe you have just a regular VRF, which is a little bit larger of a system, or you just have a standard inverter, outdoor unit. Maybe it has multiple zones there. Your EEVs will be there. So you just got to pay attention to what you are installing. You really have to pay attention when selling the job.
Absolutely right.
Another technician named Fred asks, on a mini split dual zone system, do I need to vacuum both vapor port sides or just one?
I would say both, but there's so many different varieties out there. Everyone that I've seen, we're going to have to actually recover all that refrigerant out and weigh it back in and know our charge is right. However, I have seen some of the Mitsubishi brands particular that they have individual valves at the indoor unit and the outdoor unit that allows you to isolate that one particular section. So it would depend on the brand and also the installation, in my opinion.
Yeah, so that's a great point. If you're going to vacuum a system and it has service valves at the indoor unit, you really want to pay attention to that. Make sure that the caps are on tight. If it has valve cores there, make sure that those are in ahead of time before you do any of this vacuuming. Make sure that the service valves are open. And this is if the system comes without any refrigerant inside. I mean, there's all kinds of different things that are occurring now. But So if that's the case, or maybe there is no service valves at the indoor unit, it's just flare adapters or braze joints, whatever. If you're then, after looking at that, making sure everything's open, sealed, and then you go to the outdoor unit, then you have to look at, does the outdoor unit have master service valves as well as service valves for each zone? Some systems have a pair of master service valves, and then it's just flare adapters for each zone. So each one's different. Now, most dual zone systems don't have master valves, and they just have a pair of service valves for each zone. And yes, you need to vacuum both of them either at the same time or one at a time. You can break the vacuum on one and then go to the next one and vacuum that and break the vacuum on the second one. As some of these systems, you can get away with just installing one zone, and then you have the other zone for a future install. Now, you're not going to leave it like that forever, because it's going to be running basically not as it's designed, because it can't ramp down to a low enough amount in order to run electrically efficiently. But it can be done. So yeah, you can do each one individually or both at the same time. Try not to pull through a manifold. You can use a Y fitting and just go right to your vacuum pump. Keep the vacuum gauge at a location where you can shut the valve core removal tool off and measure the vacuum of both zones or just one.
I would say definitely check that service manual for each individual one you're working with, because things are changing so fast now. Yeah. And so it's hard to give a one specific answer, because there's so many different brands that are changing stuff.
Now you're right.
There's so much information on service manuals. It's not just how to install it. There's a lot of information for that service and repair and specific procedures, and it can change from one brand to the next within its own individual brand.
Yeah. No, you're right. Yeah, absolutely. A technician named Kevin asks, my question is, when troubleshooting electric parts, where do you check and how on parts like pressure switches, temperature switches, control boards, electric heaters?
Wow, that's a loaded question. So first, I would separate it between a switch and a control. So if you're looking at a switch, like a pressure switch, you want to see, where does it open and where does it close? And so if a pressure switch, for example, high or low pressure switch will have an opening and a closing pressure, or it may just have an opening pressure plus or minus a number. But if it's if you want to check that, you just use ohms, disconnect it entirely, and you can ohm it out. You got to know what your pressure is. So if you have no pressure in there and it's a low pressure switch, it's going to open on pressure drop. So in that case, you'd be looking to see on ohms if that was a closed. You'd be looking at 0 ohms of resistance. It would be a closed switch. And if the switch was open, it'd be OL, or infinite, the most resistance you could possibly imagine. And remember, anytime you're using ohms, again, isolate it, no electrical current through there. And there's also, you can check those switches with voltage. So while they're hooked up, while it's operating, you can check voltage across those if you have a point to check. And if it's a closed switch, you'll have 0 volts. And if it's a open switch, you'll have whatever voltage that you're working with. Maybe it's 24, maybe it's 120, sometimes it's even 240, but you'll have an open switch, you'll read voltage across there.
So I would say, anytime, since this person lumped everything together and electric heaters in there, I would say one more thing, which is that the electric heaters, I would disconnect those and not be doing any troubleshooting inside that air handler while that high current is being drawn. It can all be troubleshot basically, while like electric heaters can be done with the power off using electrical resistance, like you mentioned. And so you can check all your temperature switches that way. You can see if they're closed, and if there is a high resistance value, like it is closed, but it's not 0.0 ohms. Maybe it's 1 ohm or 2 ohms. Well, that switch, the contacts could be pitted, and maybe that's the problem. And so electric heater, you can check that with the power off. And if you have OL across one of the electric heaters, well, then it's open. It's burnt apart. And I really don't want technicians' hands in there, when you're drawing high current with blower motors running and things like that whenever possible. So you really want to think about how to safely approach a situation. And in reference to control boards, what I would really like to see is basically you need to know the inputs so that you know the outputs. So are you calling for fan to turn on? Are you calling for air conditioning to turn on? Is there a limit switch open in a gas furnace? So you just have to know how the system operates in order to then troubleshoot the control board.
That's exactly right. It takes time. It takes practice, and it really takes practice, on your own time, following some schematics, taking a schematic down and following it wire by wire, line by line. Me personally, when I learned, and when I teach it this way, I'll follow one wire and then highlight just that one wire on the wiring diagram. So I know that those are connected, it's done. Then go to the next wire. And eventually, just like you read top to bottom, left to right, you can go through the whole entire wiring schematic and you'll have checked every single wire. And that really helps connect that schematic. That is a map of what's happening on the system. So once you understand how to follow the map, you understand how to get to where you're going. And it takes time, and it takes using the meter, and it takes practice, but be sure you're safe. Anytime you can, shut that power off. Always be concerned about, where your hands are going to be, where you're placed. And if you have to work with anything hot, use only one hand. And if you're checking even amps, just get a habit of using one hand so that if something does happen, it's the less likely to cause a more severe issue.
Yeah. So you bring up a good point about the wiring diagrams. I mean, really, we should be looking at this even a further back, meaning before a technician tries to troubleshoot all these things, you really want to have your component identification down. So what are these components? What do they do? What are the different variations? Because I will say in gas furnaces, for instance, the components have changed over the last, say 30 years. And so you really have to know all of these changes in efficiency have been changes in components. And so how they work. So you have to be aware of how they work before you then troubleshoot them in order to then kind of be able to work with them safely. So you really want to work with another technician, a service technician, a master license holder, and really take in a lot of knowledge, go through safety training and stuff like that, because electric is one of those things that just really sneaks up on you. You're not aware. And so you really need to be careful. And so, yeah, great points.
I think your training videos are really well. If you have the time to be able to build one of those training boards and follow that, just like Craig, like you've made, that's a great way to just actually use the hands-on in a fairly safe and fairly controlled environment to really practice without the pressure of the customer there. And you can really understand a close and open switch and checking it in different methods. It's a great way to learn.
Yeah. Yeah. And one more thing, when you are drawing or when you are testing electrical current, what I like to do is turn the power off to the system, kind of pull the wire out of a box. So when we're checking the current of something, what we can do is we can turn the power off and fish the wire out, get it accessed, and then put our clamp meter around it, put our clamp meter on the system, because it has a magnet typically, and then go ahead and turn the power back on and let it go through its sequence. And then we can watch our current. We don't have to have our hands in there. You have to think about this safely. It's a big deal. And so you really need to be aware of what you're working with, know what those ratings are. You mentioned about pressure switches, how to read those, where a high pressure switch is versus a low pressure switch. Where are they mounted at? Because then you're going to know, oh, that's a high pressure switch. Oh, okay. Well, that's not going to trip, when the system's off. It's only going to be happening when the system is running, most likely, whereas a low pressure switch, well, if the power's off and it's tripped, well, maybe we're probably low on refrigerant, so it's just knowing these things. So looking up the names of these things, watching the videos and everything like that. Absolutely. Yeah, great.
Agreed.
We have a technician named James, and he's asking a more specific question. Carrier package unit burners won't stay lit when I put the burner panel back on. So while going through the heat sequence, as soon as the indoor blower comes on, the flame goes out. Heat exchanger is okay, no cracks, and new foam tape around heat exchanger. When the burner panels are removed, the unit operates as designed.
That's a loaded question. So you said the heat exchanger is okay, but that's my first question is, how do we know? How are you checking? We just looking at a visual, or we sending a camera in there, or are we doing a combustion analysis where we can really see those changes? Because that's my first thing is when we're changing, when that blower comes on, it means we're changing how that flame is burning. And that's my first concern. And so before moving on, I'd say, hey, let's find out how we've identified that. And me personally, I like to see combustion analysis. I think anything that we work on with gas furnace for reliability reasons, that we should be doing combustion analysis so we know how that system is actually working. And then once we've confirmed that with combustion analysis, then I'll be looking at, some kind of a pressure differential. So that's where we use a manometer and we're seeing what's happening. Between the primary and secondary heat exchanger, or if we have water in that secondary heat exchanger, or something with the vent pipe, there's going to be some kind of a pressure differential.
No, I agree with you 100%. If it's only happening when the blower motor is turning on, something has to do with pressure. And so that pressure, there could be a pressure change, and that pressure change may be in the exhaust, or exchanging between the exhaust and the conditioned air, like you said. Could be between the outside environment and the inside environment where the panel is. I mean, just because you think that there's no crack or you think it's sealed, you can't rule that out. And a combustion analysis will show you that. So that's an important part. So yeah, it could be a flame rollout, it could be a flame sensor, it could be a variety of different things. And so yeah, the biggest thing is you have to have a manometer, a water column manometer, digital one. Make sure that you are aware of what's happening. Combustion analysis, digital water column manometer. You're going to figure this out.
I took a class several years ago now that it was for combustion analysis and also for carbon monoxide safety. And that was a great class. I really thought I understood gas furnaces. And when I took that class, I realized there's a whole nother level. And I strongly suggest anybody taking one of those classes, reading the books that go with that. And look, I'm not one who just likes to sit down and read a book, but there's so much valuable information and it tells the hows and the whys and some of the unexpected stuff. We can have a furnace that's working really good right now, but when we leave, the conditions of the home can change and can cause an unsafe condition. So by understanding combustion analysis and carbon monoxide, we get the bigger picture of that house and we make sure that we're protecting our customers all the time, not just while we're there, checking a little box.
Yeah. It's not just good enough to get the system running. There could be a lot of different things going on. Liabilities at stake, people's lives are at stake. There's a lot to it. And so, yeah, you want to be as effective and knowledgeable as possible and do the best job. And that's going to make you more valuable as a technician. I think it really will, because then you're going to be the one that knows what's going on. You're going to be the one that people call when there's a problem. And so, yeah.
Absolutely.
A technician by the name of Carl asks, what happens if you permanently take off the sensing bulb from the TXV or from the line?
Kill compressor. That's the short answer of that. So what you're doing is you're trying to by doing that, they're really fooling the TXV. And the TXV is trying to monitor not only that suction line temperature, but also the suction pressure. And it's trying to control the amount of superheated vapor. If we know how much superheat we have, we know that we have the right amount of refrigerant in the coil and the right amount of vapor to that vapor pump. That compressor needs to breathe in a superheated vapor. So if we take that bulb off, the sensing bulb off that line, it's reading a higher temperature. So the TXV is looking at the pressure and that higher temperature, and it says, man, my superheat's too high. So the TXV opens and lets more refrigerant into the evaporator coil. Now, if you're just looking at the delta T across that evaporator, you're thinking, oh, it's working better. There's more refrigerant in there, more refrigerant changing state. It's cooling better. And if you're only looking at that, that's true. But the problem is your superheat drops off very quickly, very sharply, and you end up getting a saturated vapor liquid mixture to the compressor. And that compressor is a vapor pump. Now we got liquid coming into it. It's either going to get into the pumping action of the compressor and kill it immediately, or more than likely it's going to actually wash the oil away from the bearings. And as that compressor is running, it washes the oil from those moving parts and the bearings start going bad and it causes long-term damage. So I hear technicians say, well, I do that all the time and I've never had an issue. You don't see the issue, but the issue is there and the customer is going to have to be paying for it.
Yeah. So you could look at this a couple different ways. One, you could look at it where they say, can I permanently remove the sensing bulb? Meaning like cut off the line. And of course, no. And so if you did that, then you're not going to have any opening force on the TXV. And so it's going to have a high superheat and it's going to be starving the evaporator coil for refrigerant. And you're going to have a extremely high superheat. And that's also not going to be good for the compressor life either. So if you just disconnected the bulb from the vapor line, which may have been anywhere from say 32 degrees to 50 degrees Fahrenheit, or it just depends on the heat load inside the building at that point in time. When you remove that, well, now it's removed and it's sitting maybe within a 70 degree inside of the building, right? If it's in a closet, if it's up in the attic, maybe it's 120 degrees up there. And so like you said, it's going to apply more opening force on the head of the TXV, and it's going to allow more liquid refrigerant in because it thinks that there's a crazy high heat load, meaning the temperature of the air crossing that indoor coil. And the TXV's job is to maintain superheat, not to maintain the vapor pressure. So
that's exactly right. And really take your time and really understand how TXVs work, because there's so much involved with TXVs. And unfortunately, they're misdiagnosed all the time. And so there's a lot of jokes around anything, there's something wrong. So even a gas furnace, people say, oh, TXV. And it's kind of funny, but it's really not, because they're so often misdiagnosed. People don't really understand how they work. And they just look at the TXV, they don't understand that TXV works. So that must be the problem. So if you really understand all that's happening with the TXV, take the time to really look in those internal components and see how it's reacting and responding to temperatures and pressures and airflow. That's one of the big ones. You can really see, once you really understand how a TXV works, they really rarely fail. And there's usually something, if they do fail, something caused those. You want to find out why, and let's solve that problem.
Yeah. A lot of times it's a clogged strainer right at the inlet, or it could just be the pin is clogged with gunk. I mean, and that could have been from maybe somebody not flowing nitrogen while brazing. There's a lot of reasons why a TXV might fail, but a lot of times it's due to outside circumstances. And of course, the older TXVs had the steel heads, and they would rust and potentially leak refrigerant out, which would then you wouldn't have the opening force. But the newer TXVs, they're not like that. They're a lot of times they're stainless steel, and so you don't have that problem. And so it's usually from outside circumstances. So yeah, great. Well, I think we answered a lot of questions today, and I just thank you so much for coming over and just being here with us. And I always enjoy hanging out with you. And you're a great mentor, a great friend, and yeah, I just love having you over.
Well, you know how much I appreciate you. I can't thank you enough for our friendship and our talks and our conversations. I love how you're helping the community, and I love that you guys have questions. These questions you have, the fact that you want to learn. That is so important. And we want to help you. Both of us, we're here because we want to help the community, help the people understand. And I think it's great that you're asking questions. Keep asking questions, keep learning. And with a great guy like Craig here to helping you out, you can't go wrong.
Make sure you check out Ty's channel over on YouTube, and he's got he's on basically all social media. So you just look him up, Love to HVAC and Ty Branaman. And you can also check out some of our resources over at acservicetech.com as well. And loved having you here, brother. Thank you so much.
Thank you.